In this video, we're going to be looking at beginning chapter 6, solving system of equations, and these are our notes packet. And we'll start with 6.1, solving systems by graphing. So we'll start with our essential question. How do I solve a system of equations by graphing? So first we'll need to know what a system is. And a system is two or more equations with two or more variables. And a solution of a system is an ordered pair x, y that satisfies both equations. So what that means is if I plug an ordered pair in to both equations, is it true for both of them? So if I plug 2, 1 into the first equation and then 2, 1 into the second equation, do I get true statements from both? If I do, then I have satisfied both equations, and this ordered pair is a solution to this system. So what we'll do is let's check this. We'll plug in 2, so we'll have negative 7 times 2 plus 1 equals negative 13. Just plugging in 2 for x and 1 for y. Then I'll solve and I get negative 14 plus 1 equals negative 13. Negative 13 equals negative 13. That's true. So one of them is true. So far we're halfway there. But we need both of them to be true for this to be considered a solution to the system. So let's look at this one. And then I'll plug in my x and my y. So now I'll have 2 minus 5 times 1 is equal to negative 3. 2 minus 5 equals negative 3, and we get negative 3 equals negative 3. So that's a check. So we can say, yes, 2 comma 1 is a solution to the system. So let's look at number 2. Plugging them in and then simplifying. So we'll say 2 times 4 minus a negative 3 equals 11. So that becomes 8. 2 times 4 is 8. Minus and minus is plus 3 equals 11. We get 11 equals 11. Check. So I'm halfway there. One of them is correct. Remember, I need both to be true for this to be a solution to the system. So let us check the other equation, plugging in, and I get 4 minus 3 times negative 3. 4 minus 3 times the negative 3 is equal to negative 5. So we have 4 with a minus 3 times negative 3, so it becomes 4 plus 9 equals negative 5, and we get 13, which does not equal negative 5, so that one did not work. So we know that 4 negative 3 not a solution to the system. I needed to satisfy both. It checked off on one. If this ordered pair worked for that first equation, but it did not work for the second equation. So if it's not both, it's not a solution. Okay, so let's get some definitions. A consistent system is a system with at least one solution. So if it has one or more solutions, it's a consistent system. Inconsistent is a system with no solution. So independent system is a system with exactly one solution. And a dependent system is a system with infinitely many solutions. So if it's a consistent system, it can be independent or dependent. But an inconsistent system cannot be either one, because independent, dependent is implying that there is some kind of solution. So what we notice is that when a point satisfies both equations, that means it's a solution to the system. So where would that exist if I was graphing them? Well, what would it mean for one point to be a part of both graphs? So let's examine this. So I'm going to put this one in blue, and I'll put red for my second equation. So we're going to graph this, starting at my y-intercept of 3. And then I have a slope of 2. Remember, there's a hidden 1 underneath, so it's 2 over 1, so I'll go up 2 over 1, or I could go down 2 and left 1. And we'll connect these dots. We'll want to make sure that we're very accurate when we're connecting the dots, because it's important that we draw our lines very nice and neat so that we can see exactly where they cross. So I can go down 2 and over 1, connecting my dots, like so. And now let's graph this next line in red, going to my y-intercept of -2, down 2. And then remember, I have this over 1, -3 over 1, so I'll go down 3, 1, 2, 3, and then to the right 1. Or I can go in the reverse and go up 3 and then left 1. Connect these dots. Now, what would be the solution to this system? Well, the solution to this system is going to be this point that they both share. Because this point is the point that when I plug into both these equations, I'd get a true statement. So the solution is that point of intersection. which for this problem would be -1, 1. Like that. That's that point right there. This point satisfies both equations. So you graph the lines, and then you find the point where they intersect. Let's go ahead and flip to the back. I'm going to show you a couple more examples, and then we'll move on. So let's look at number 5. So all we're going to do is we're going to graph both lines, and then we'll find the point of intersection. But before I can graph both lines, I need to be, so let's put a little star to the side. So must be in y equals mx plus b to graph. So let's go ahead and get into y equals mx plus b. I will subtract 4x from both sides. So now I have -y is equal to -4x plus 2. Then we'll divide everything by -1. And we'll have y is equal to 4x minus 2. And we'll make sure we have our hidden 1 there. So there's that first equation. Let's go in and get our second equation. I'll subtract 2x from both sides. And we'll have y equals -2x plus 4. Y is positive and it's by itself, so we're good. Y is positive and by itself. So let's graph. Let me put my over 1 for my slope. So we'll first graph this line, the green line. I'll start by going down 2. And then my slope is up 4 and to the right 1. 1, 2, 3, 4, and to the right 1. Let's connect our dots. Then my purple line started at +4. 1, 2, 3, 4. And then we'll go down 2 to the right 1. Down 2 to the right 1. And now we see where we intersect is right at this point. So that point of intersection would be over 1 up 2, so 1 comma 2. So my solution is (1, 2). Okay, now I'm going to skip to 7 and 8 because I just want to look at a couple of special cases and then we'll be done. So 7 and 8. First we'll want to get y by itself, so we have y equals mx plus b. So we'll use, so first I'll subtract 4x, and I'll have -2y equals -4x plus 6. Divide everything by -2, and we get y equals 2x minus 3. There's our hidden 1. Let's go ahead and solve our second equation, and then we'll graph both at the same time. So I'll subtract 2x, and I get -y equals, let's cross this one off because we won't be able to use it. So this is just -4 right here, -4. So -y equals -2x minus 4. We'll divide everything by -1, and I'll get y equals 2 over 1x plus 4. Let's see what happens when we graph these. I'll graph the green one first, go down 3, then up 2 over 1, up 2 over 1, up 2 right 1, connect my dots. And then with my purple, if I start at the 4, 1, 2, 3, 4, and if I go up 2 over 1, I'll go off my page, so I'm going to go down 2 and left 1. Down 2, left 1, down 2, left 1, down 2, left 1. Connect our dots. And so when the lines are parallel, equal slopes, parallel lines, this is where we have no solution, because they never intersect. So no intersection, no solution. Now let's look at number 8. So first thing we want to do is get both lines into our y equals mx plus b form. So I'll subtract 2x from both sides. We'll have y equals negative 2x minus 3. Now let's do this to the other one. Subtract 6x from both sides. And we'll get 3y is equal to negative 6x minus 9. Divide everything by 3. Oops. And I'll have y is equal to negative 2x minus 3. Now notice the two equations. Now they're exactly the same. So what's going to happen when I graph both of them? Well, they're going to overlap. So when we have overlapping lines, this is that idea when I can have infinite solutions. So we'll say overlapping lines, infinite solutions. And that's how we can solve systems of equations by graphing.